Okay, welcome to today's explainer, where we're going to pull back the curtain on the invisible algorithms, the physical networks, and the really incredible mathematical marvels that are secretly powering our daily lives. You know, we interact with this magic glass in our pockets every single day, completely unaware of the massive, complex symphonies playing out just beneath the surface. Well, today, we are going to change that. Here is our roadmap for today. We're starting with smartphone secrets, then moving into the invisible security mesh, followed by world-moving algorithms inside the AI engine, and finally, decoding the unseen. Let's get right into it. Starting off with Section 1, smartphone secrets and some hidden hardware hacks. So, the absolute easiest way to become a power user isn't to learn how to code. It's actually just understanding the physical limits of the hardware you already own. By understanding the physics, you can literally optimize your entire digital household in minutes. Take your smartphone battery, for instance. It degrades primarily from heat and high voltage stress. If you just enable that 80% charge limit in your settings, you completely stop the damaging trickle charge cycle that is basically cooking your battery overnight. Same goes for Wi-Fi. Did you know your microwave leaks 2.4 gigahertz radiation? That totally blocks older Wi-Fi signals. Just moving your smart TVs and laptops over to the 5 gigahertz band solves the buffering instantly. And for your smart home, look for the new Matter protocol. It allows devices to communicate locally via a self-healing thread mesh. What does that actually mean for you? It means when you tap a button to turn on a light, it happens instantly, even if your internet completely goes down. This brings us to a huge pain point: the photo storage trap that catches millions of people off guard. You have to understand that iCloud acts as a direct, real-time mirror. So if your phone is full and you delete a photo on your iPhone just to save some local space, iCloud instantly deletes it from their servers too. Poof, it is gone forever. Google Photos, on the other hand, is built like a secure, one-way vault. Once your photo is uploaded there, you can safely hit their free up space button to wipe the physical file off your actual phone without ever losing the memory. It's a lifesaver. Now, if you truly want to master your phone and get your time back, you've got to stop begging AI and start being the boss. You can use no-code platforms like Zapier to act as the digital glue connecting apps like Gmail and Google Sheets. But the real secret sauce here is in how you prompt. By forcing these large language models into highly specific personas, saying something like, act as a veteran travel planner, and then chaining your instructions step by step rather than just dumping it all at once, you dramatically improve the output. You can essentially automate hours of daily chores this way. All right, moving on to Section 2, the security mesh and the invisible protections around us. So, do Apple AirTags actually track you using GPS satellites? You might assume they use battery-draining GPS modems, right? But the reality is way more clever. They rely entirely on passive Bluetooth beacons. These little devices sleep almost constantly, only waking up for a tiny millisecond to broadcast a public key to literally a billion passing smartphones out in the wild. It's those strangers' phones that encrypt the location and send it up to Apple. And to keep things private, the AirTag rotates its public key every 15 minutes. That makes it mathematically impossible to track a single tag over time unless you own the encrypted private key on your specific phone. We see a very similar, brilliant security model whenever you use Apple Pay. When you tap your phone to pay at the grocery store, your real credit card number, the primary account number, is actually never exposed to the merchant. Instead, Apple Pay uses a process called tokenization. The network issues a device primary account number, which gets locked deep inside a physical chip on your phone called the secure element. So when you pay, it just generates a one-time dynamic cryptogram. Even if a hacker intercepts that specific NFC transmission, it is totally useless for a second purchase. This brings us to passkeys. And look at how they mathematically kill phishing attacks. Traditional passwords rely on what's called a shared secret. You know it, the website knows it, which means a hacker can steal it. Passkeys, though, use asymmetric cryptography. Your device generates a private key that never leaves the secure chip on your phone, and a public key that gets sent to the website. When you log in, the website sends a mathematical puzzle, your phone signs it locally using Face ID, and access is granted. Absolutely no secrets are ever shared across the internet. Next up is Section 3, moving the world, focusing on algorithms in action. Let's scale up from our pockets to the streets. If Uber used a simple, greedy first-come, first-served algorithm, you'd have hundreds of riders requesting cars at the exact same millisecond, causing total double-booking chaos. To prevent this, Uber uses something called disco batch matching. They map the Earth into tiny geometric grids using S2 geometry, group the incoming requests into 2 to 5 second batches, and run a massive global optimization algorithm. To guarantee a driver isn't booked twice, they rely on atomic database locks. If two requests hit simultaneously, the database atomically rejects the second one, maintaining perfect system integrity. And here's where it gets even cooler. Before that Uber even starts driving towards you, Google Maps is already doing the heavy lifting to predict the real-time traffic jams your driver is about to face. It does this by constantly analyzing smartphone telemetry from devices on the road, comparing that against historical baseline modeling, and feeding it all into DeepMind's graph neural networks. It literally sees the future of the traffic grid. Over in the realm of culture and social media, there's a reason TikTok feels so insanely addictive. It runs on an architecture called monolith. Older social networks usually update their recommendation algorithms overnight in massive, slow batches. TikTok's monolith, though, trains online in near real time. The exact second you skip a video or rewatch one, a system called the joiner feeds that behavioral data right back into the model. By using what are called collisionless embedding tables, the system gives you a totally unique mathematical shape, a highly specific digital fingerprint, and it updates your preferences in minutes, not days. Back out on the physical roads, we're seeing two brilliant, completely contrasting philosophies for self-driving cars. Waymo relies heavily on pre-scanned, centimeter-accurate HD maps and multimodal sensor fusion. They combine expensive LiDAR lasers and radar with standard cameras to build a highly structured view of the world. Tesla, on the other hand, totally rejects LiDAR and HD maps. They use a vision-only approach. They basically convert 2D camera pixels into 3D Minecraft-like blocks using what are called occupancy networks. The car's brain doesn't even necessarily care what the object is. If a digital voxel block is occupied, the car just knows not to drive there. Section 4. Inside the AI engine. Let's unpack some neural networks. We need to understand that large language models do not read English. They read math. First, the words you type are broken into smaller pieces via byte pair tokenization. Then, they get mapped into massive geometric spaces as high-dimensional embeddings. Because of this, the concepts of dog and cat literally live near each other in this mathematical space. Finally, the transformer architecture uses a mechanism called self-attention. It calculates query, key, and value vectors to weigh the relevance of every single word against every other word simultaneously, allowing it to magically understand context. Image generators like Stable Diffusion use a completely different trick. They don't actually paint pixels on a canvas. They're trained by taking real photos, destroying them with Gaussian static, and then learning to reverse that destruction. To save massive amounts of computing power, this all happens in a compressed latent space. So the AI acts like a mathematical sculptor. It looks at pure static, and guided by a text vector from a system called CLIP, it gradually subtracts the noise step by step until your prompted image finally emerges from the chaos. Now, standard language models sometimes hallucinate or make things up because their memories are frozen in time from when they were trained. To solve this, AI answer engines use something called Retrieval Augmented Generation, or RAG for short. When you ask a question, the system hits pause, runs a live web search, filters out all the junk, packs the relevant paragraphs into its memory window, and then forces the AI to write a perfectly cited summary in milliseconds, basing its answer strictly on that retrieved ground truth. And finally, Section 5, Decoding the Unseen, where we look at the cutting-edge frontiers of AI. These exact same neural networks are now breaking out of our phones and unlocking the deepest mysteries of human history. In 79 CE, Mount Vesuvius erupted and carbonized an entire library of papyrus scrolls, basically turning them into lumps of coal. But recently, the Vesuvius Challenge achieved the impossible. Using 3D CT scans from particle accelerators, researchers virtually segmented the rolled-up layers. Then, they trained machine learning algorithms to spot microscopic ink crackles and textures, successfully detecting invisible carbon ink on carbonized paper. We are now reading lost philosophical texts that literally haven't been opened in 2 millennia. Absolutely wild. And it's not just history, it's nature. The Earth Species Project is applying this to biology. Remember how we just talked about language models mapping words into geometric spaces? Well, it turns out different human languages share remarkably similar conceptual shapes, which allows for translation without a dictionary just by aligning those geometric blobs. Researchers realized that if they map animal sounds into these same high-dimensional spaces, they can actually translate interspecies communication simply by aligning the semantic geometry of their concepts with ours. I know that sounds like science fiction, but it's happening right now. Project CT has been processing millions of acoustic clicks from sperm whales. By using AI to solve the complex underwater cocktail party problem, basically isolating single voices from a chaotic pod of whales, they discover that whales communicate using a highly structured 156-character phonetic alphabet. They alter rhythmic patterns using tempo, rubato, and ornamentation. It proves there is an incredible underlying grammatical complexity to how they speak. Even more remarkably, we can now use AI to decode the human mind non-invasively. Researchers at UT Austin and Osaka University are taking fMRI blood flow scans and mapping them directly to GPT in Stable Diffusion. While a person is inside a scanner just listening to a story, the AI can actually decode the semantic gist of their thoughts, outputting translated phrases like, "I woke up and realized I had wings." They can even map the visual cortex to reconstruct a photorealistic image of exactly what a person is seeing in their mind's eye in real time. This mathematical ability to track complex structural relationships is exactly how Google DeepMind's AlphaFold solved the 50-year protein folding mystery, which, by the way, recently won a Nobel Prize. By looking at evolutionary fingerprints across millions of species, its evoformer and invariant point attention modules calculate the exact 3D Cartesian coordinates of amino acids. This allows scientists to predict the shape of basically every protein known to science in mere seconds. So, the next time you tap your phone to pay for coffee, ask an AI a question, or request a ride, I want you to take a moment to really marvel at the invisible symphony of algorithms, geometry, and hardware you are setting into motion. We are surrounded by an unseen architecture of incredible complexity. The real question is, now that you know how the matrix actually works, are you going to let it program you, or are you going to program it?